Now that we have a better idea about where we get these free charge carriers in a semiconductor material, we're ready to start looking at how we get currents from these free charges. So let's recall that in general, our current can be defined as I equals dq dt, so change in charge over change in time. And so what that tells us is that anytime we have charge movement, that results in a current. So charge movement results in current. And so that's true for any material or any medium, not just semiconductors. So for our semiconductors, we're going to see we have two relevant current processes. So let's just say here, two relevant processes, and we're going to look at one in this video, and we're going to look at the next one in a following video. But the two processes are drift, which is what we're going to consider here, and diffusion. And depending on the conditions, typically we're going to have one that is dominant, or during certain times we might have one that's dominant over the other. And that's something that we're going to talk about in more detail once we look at actual device structures. So let's go ahead and look a little closer at this first current process, our drift current density. And so notice we're talking about current density as opposed to just current. And so what that means, we're going to have this symbol, which you might or might not be familiar with, capital J, so that's our current density. And so in general, that's equal to our current, I, divided by our cross-sectional area, A. And typically in semiconductor physics, the units that we'll end up dealing with, so this is equal to dimensionally, so I have an equal sign with a little d over it for dimensions. So dimensionally, this is going to be equal to amps divided by square centimeters. So that's sort of typical units that you'll see for this. Okay, so what we have for this drift current density, though, is we have movements of charge carriers resulting from some applied electric field. So movement of charge carriers due to applied electric field, which I'm just going to put E with an arrow over it for electric field. And so ultimately this electric field is created from some voltage. So simplistically, if we say we have a uniform field, we can say that our electric field is equal to voltage divided by the distance between sort of two parallel plates if we're considering the simplistic case. Right now, don't worry about that too much, but just know ultimately that electric field is going to be resulting from a voltage we apply to the semiconductor. So let's consider sort of just a piece of semiconductor here. Let's see if we can get a nice square. There we go. So let's say we have a piece of semiconductor, and within this semiconductor we have some applied electric field. So let me make this maybe a little larger to distinguish it. So we have some electric field which is pointing in this direction here. So remember, we're going to have free charge carriers in this semiconductor. Whether we've doped it or not, we're still going to have some carriers if it's above absolute zero. So let's say we have some electrons, so electrons here, and in the presence of an electric field, remember, positive charges are going to move in the direction of the field, negative charges are going to move in the opposite direction. So any free electrons are going to be moving, the way I've drawn this, from right to left. So in contrast, if we have holes, which are positively charged, they're going to be moving in the direction of the electric field. So the way I've drawn it here, they're going to be moving from left to right. And what we're going to see is we're going to have to consider both of these things together in order to determine what our drift current density is, J. And so our drift current density is going to be in this direction. And so the reason I can say confidently it's in this direction is, of course, we have our conventional current direction is the opposite of the direction of electron flow. So both this electron movement and this hole movement are contributing to J going from left to right. Okay, so again, we know that that J is going to be comprised of those two components, one due to electrons, one due to holes. So what we can say is that our overall overall drift current density is equal to an electron drift current density plus a hole drift current density. So J sub n and J sub p respectively. So let's take a closer look at each of those two component parts. So first let's look at our electron drift current density. So electron drift current density. So with this electron drift current density, we're talking about this J sub n term. So J sub n, we can say is equal to negative Q in V sub d n. So let me define what each of these terms are. So Q is the magnitude of the charge on our electrons. So of course we have a negative because our electrons are negatively charged. So I'm just going to say this is charge of electron. So we'll see an example in the next video, but that's 1.6 times 10 to the negative 19. And so remember, as I mentioned in a previous video, in the Niemann textbook, he uses the symbol E for charge of the electron. So just in case you're looking there and get confused, that's what the difference is there. The N is the electron concentration, or the density of our electrons. So that's how many electrons we have per cubic centimeter is the typical units for that. And then we have our V sub dn, which is our drift velocity, and that's equal to negative mu sub n times E. And so this is our electron drift velocity. So of course I've just introduced a new term here as well, so let's define that also. So this mu sub n is equal to, or equivalent to, our electron mobility. And then of course our E is the electric field strength, so the magnitude of the electric field. And so I'll come back and mention some other notes about this mobility term a little later. But essentially this electron mobility is how easily the electrons are able to move throughout the lattice. We notice that this velocity has a negative sign in it as well. The reason for that is, of course, because the electrons are going in the opposite direction of our J. So our electrons are going from right to left, whereas our J is going from left to right. But what we're going to see is that this negative sign will cancel out with this one, so that overall we have a positive value here. So let's go ahead and actually write that out. So we have our J sub n is equal to negative Q times n, and then let's substitute in for that velocity. So that drift velocity is negative mu sub n times E. Our two negative signs cancel out, and we're left with Q in mu sub n times E. So that is the expression for our electron drift current density. So similarly, we could look at our whole drift current density. So whole drift current density. And so for our whole drift current density, now we're talking about this J sub P term. So coming back here, we've got this J sub P. And so this is going to be equal to Q times P times V sub dP. And so let's just go ahead and say here our P is equal or equivalent to the concentration of our holes. Our Q, of course, is still just the charge of the electron. Notice now we don't have a negative sign out front because the charge is positive. And this V sub dP is our whole drift velocity. And we could also write this in terms of a whole mobility. So we could say this is QP times mu sub P times E. So E is still our electric field strength. And now we have this mu sub P, which is our whole mobility. And so that's just how easily the holes are able to move throughout our semiconductor lattice. So simplifying this, well, not simplifying, just getting rid of that parentheses, we can just say this is QP mu P E. So it looks sort of the same form as we have for our electron drift current density. And so one thing to note that I forgot to mention earlier is, of course, if we're looking at sort of this combined expression here for our overall current density, we can see it, of course, consists of these two parts. And based on the fact that these two equations depend on the concentrations of N and P, we can see that this is going to vary, and typically one of these two terms will dominate depending on how our material is doped and to what level. So just something to keep in mind, and again, we'll see that in the example, and you'll see that in some homework problems as well. So let's go ahead and explicitly combine these two terms to get an expression for our overall current density. So again, our overall current density is J is equal to J sub N plus J sub P. So substituting in our two expressions, we have Qn mu sub N times E plus Qp mu sub P times E. Well, so what we can actually do is we can write this as equal to sigma E, or we could also write it as 1 over rho times E, where we could define sigma as equal to Q in mu N plus Qp mu P. And so you might have seen this term before. This is called the conductivity of a material. And so if you've seen that before in physics or chemistry, you're probably just given that as a material property. You might also be familiar with rho. So rho, which is of course, as we can see, not 1 over rho, 1 over sigma, is our resistivity. And so in previous classes, you might have seen how you can relate resistivity to resistance. So for example, if we have a uniform material, we can say resistance is equal to rho times the length divided by the cross-sectional area. So again, in previous classes, you might have seen this conductivity given as just a material value. So maybe for this material, conductivity is X. It's some fixed number. But what we can see is we have N and P, which are our electron and hole concentrations respectively. And remember that through the process of doping, we essentially can control that. So what this means is that we can control material conductivity with doping. So can control our material conductivity, in other words, our material properties, how well it conducts with our doping process. So that's a pretty cool thing. And so what we're going to see is using this and sort of combining different areas and taking advantage of certain sort of natural phenomena, we can create a lot of cool electronic devices. So one other thing to note too, in terms of this equation, there are sort of physical limits that apply to this current density equation, and we're not going to get into it in this class, but I want you to at least be aware of it. So those drift velocity terms are V sub, let's see, they were V sub dp for our hole drift velocity and V sub dn for our electron drift velocity. Those are actually going to saturate at some value. So our drift velocities saturate at about 10 to the 7th centimeters per second. And so by saturate, I just mean that's sort of the upper limit. We can't have our charge carriers moving faster than that in our semiconductor. Another thing to point out is that the mobilities, so our mu sub n and our mu sub p, so our electron and our hole mobilities, are dependent on our material and on the temperature of the material, as well as other things such as dopant concentration. So dependent on material temp, dopant concentration, etc. And so that kind of makes sense because remember we said our mobility is how easily can these things move about the crystal. Well, let's say I think the easiest one to visualize as our dopant concentration. So if we start putting more dopants in there, we start sort of crowding things up, it's of course going to become harder for our carriers to move about. So again, these aren't things that we're going to really consider in this class, but just something to be aware of.